Hello, and welcome to this lesson on scientific notation. This will be the first of 3 different lessons on scientific notation. This lesson is focusing on just understanding what scientific notation is, being able to convert it from standard form to scientific notation and back. The next lesson will be all about addition and subtraction of scientific notation. And then the last lesson will be all about multiplication and division of scientific notation. So let's get into it. The essential question says, how do I use scientific notation to represent very big and very small numbers? Your previous experience with scientific notation probably only talked about very big numbers, like in the Did You Know? Did you know that the weight of the Earth is approximately 1.317 times 10 to the 25th pounds? So if you are like an actual rocket scientist and you have to account for the mass of the Earth in all of your calculations, like to shoot rockets in outer space, you have to deal with gravity and stuff, it would be much, much easier to use this in your calculations instead of writing this in all of your calculations. So that's one of the main reasons for scientific notation, is because not everything in real life is like a size that we can measure very easily with a ruler. Some things are incredibly tiny. An atom, a nucleus of an atom, even smaller. Or really big, like a galaxy, a solar system. If you're trying to measure the solar system in miles, which nobody does that, they'd use kilometers anyways, or light years, it still can be incredibly large, and to write these numbers on just its standard form, like regular numbers like this, would take a very long time and would waste a lot of paper. So we have 2 vocabulary words here. We have scientific notation and standard form. So scientific notation is just a way of writing very big or very small numbers. It always looks like this. So this is kind of like the format, the formula, so to speak, where the C is a number between 1 and 10. So that means that this C has to essentially be a 1-digit number, like 1 point something, 9 point something. It cannot be 10 point something. It cannot be 0 point something. It has to be a 1 point, 2 point, 3 point, 4, 5, 6, 7, 8, up to 9 point something. No tens, there's no 2 digits in front of the decimal, or more allowed. So C is a 1-digit number, and N is an integer, N being our exponent. We've been talking about exponents. Our exponent is an integer. That's a positive or negative whole number. No decimals, no fractions allowed for those exponents. Okay, so these numbers are both in scientific notation. This number is, he's negative, but this number is very, very tiny. It's like 0.000000934 or something. I didn't actually count out my zeros. Standard form is just the way we'd normally write a number. It's with the commas. It's writing out really big. So like 12,445. That's standard form. And 0.00083. That's standard form. Okay. So the first thing we're going to look at here is being able to write a number in scientific notation. Now, I'm going to say that the method that I'm going to use is probably a little different than what you've been taught before. You've probably been taught that you count decimal places and then you write the number out. Okay. I'm going to teach you a very specific method because addition and subtraction is ugly in scientific notation. So I'm going to teach you a method that will work and we'll be able to expand when we get to addition and subtraction, and it will still work. It will consistently work. Okay. I love things that are very consistent. One method that works all the time. This is one method that works all the time. So here's what we're going to do. I'm going to start to make this look like scientific notation by adding a times by 10 to the power of 0. Now we learned in one of the previous lessons that anything to the power of 0 is 1. So really, I'm just saying this stuff times by 1. So I didn't change its value. I didn't make it anything other than 86,700,000. It's still that. I'm just adding this to start to make it look like scientific notation. Now, in scientific notation, we would want this number out front to be a 1-digit number. We want one decimal place, one value in front of the decimal, which means we would want the decimal to be right here, 8.67. So here's what I'm going to write. I'm going to write 8.67 times by 10. I'm not going to put a 0 this time because we're actually going to figure out what he should be. And how do we know? Well, we had to move the decimal from where it started, this original number. The decimal was here at the end. And we had to move this decimal a bunch of places. We moved it 1, 2, 3, 4, 5, 6, 7 places. We moved it 7 places, and the value of this number got smaller. Right? It was 86 million, and now it's 8.67. It got smaller. But there's a cool little thing. When this value gets smaller, my exponent gets bigger by the same number of places. So, excuse me. So this piece got smaller by 7. If my exponent gets bigger by 7, what would we get? Well, 0 bigger by 7 is 7. And that's probably the same thing you got when you did it your other method using, if you had another way of doing this in scientific notation, okay? But this idea of making this guy smaller and this guy bigger, or how they move kind of opposites of each other, is going to be kind of a pretty big deal this unit. So that's why I'm starting to show you at the very beginning, and we're going to use it pretty much every single problem. All right, letter B. So I'm going to add a times by 10 to the power of 0. I'm going to make this a 4.924 times by 10 to the something. So I made it start to look like scientific notation. I moved my decimal from where he started to where I want him. I want it between this 4 and the 9 to make this a 1-digit number, 4.924. Now, I can see that my decimal piece, the value, got smaller by how many places? 1, 2, because this is where the decimal started, so I'm moving it 1, 2 places. So smaller by 2, so my exponent gets bigger by 2. And 2 bigger than 0 is 2. And we're done. So you see, this doesn't actually have to be like a big, long, complicated process. It can be very quick, and you'll see when you get a practice doing this, it is very, very quick. And you'll hear me a lot of times when I'm in some of the later problems, I'm trying to figure out what to do. I'll even say, okay, if this guy gets bigger by 3, this guy gets smaller by 3. And I hear students saying it to themselves all the time in class as well. It's a very good memorization technique. All right, I'm going to have you try these next 2. There they are. I got them on the screen for you. So go ahead and pause the video, change both of these numbers to scientific notation, and when you're ready to continue, hit play, and we'll do it together. All right, letter C. Times by 10 to the power of 0. I want this to be a 1.0. We really don't need the 0.0 at all. I mean, we could leave it without it. I'm going to make it a ghost 0.0. Times by 10 to what power? Well, this piece got smaller I'm abbreviating a little bit because I don't like to write out the word bigger and smaller every time. This piece got smaller by how many places? Well, in this number, this is a whole number, the decimal would be at the end, right here. So it moved 1, 2, 3 places. So it got smaller by 3. So my exponent gets bigger by 3. There it is. 1 times by 10 to the third power. Last of these, we add a times by 10 to the 0 to make it start to look like scientific notation. Put the decimal where we know it needs to go. So it needs to be between those first 2 digits right here. Since this is a whole number, the decimal started at the end and we moved it 1, 2, 3, 4 places. We moved it 4 places and the value of the number got smaller. So then my exponent is going to get bigger by 4. And that's it. Now, you may not have ever done a problem like this before, so I want to change this into scientific notation. This is a very, very small number. And in the past, when I used to teach this, before I came up with this new method, it'd always be hard for students to remember, oh, do we move the decimal to the left or do we move the decimal to the right? And when you're converting from standard form and scientific notation, and it was different if it was a big number versus a small number, and it was a lot of different memorization. With this new technique, though, check this out. You add your times by 10 to the power of 0. We know the decimal needs to be between the 3 and the 2. This needs to be a one-digit number, so 3.2 times by 10. Okay, this number here is getting bigger. It went from 0.0000, that's a very, very small number, to 3.2. So its value got bigger by how much? 1, 2, 3, 4, 5. It got bigger by 5 places, which means my exponent is going to do the opposite. It's going to get smaller by 5. Well, what is 5 smaller than 0? Ooh. You have 0 and you go down by 5, you're at -5. And that's it. This does have a negative exponent. Negative exponents, you'll see, with pretty much be all 4 of these problems we're doing on this page. You get a negative exponent when this value is smaller than 1. If it's a 0 point something, you will get a negative exponent. Okay, times by 10 to the power of 0. Make this the decimal we want, 1.62 times by 10. This piece is getting bigger by how many places? 1, 2, 3, 4. Bigger by 5. So this piece gets smaller by 5. 5 smaller than 0 is -5. That's it. All right. So why don't you pause the video and you try 2 on your own. Letters G and H. When you're ready to continue, hit play, and we'll do them together. All right, letter G. You added a times by 10 to the 0. You made this a 7.3. This piece got bigger by 1 place. You move the decimal 1 time. And that means your exponent is going to get smaller by 1 place. -1. Done. Add a times by 10 to the 0. Make this the decimal we want it to be, 6.923 times by 10 to the, let's see, this piece is getting bigger by 1, 2, 3, 4 places. So my exponent gets smaller by 4, -4. And we're done there. So that's how you change a number from scientific notation or from standard form into scientific notation. Each of these numbers originally was in standard form. It's how we normally write a number with commas and decimals and 0.00 stuff. And we change it into scientific notation. Okay. Now, the next set of numbers are not quite scientific notation. That is not scientific notation because this number is 834. We're not allowed to have that. This needs to be 8.34. Okay? So we're going to take each of these numbers and fix it, put it into proper scientific notation. And it's if you followed along with this method I've showed you, it's very easy. So we already have a times by 10. Check. I'm going to put the decimal where I know it needs to go. 8.342. So the decimal goes between the 8 and the 3, between those first two digits. This guy got smaller by how many? 2 places. I mean, it was 834, it's 8.34. The value of the number itself got smaller by 2 decimal places, which means my exponent is going to get bigger by 2 decimal places. And 2 bigger than 3 is 5. Without this method of the getting bigger and getting smaller, this problem would have been very complicated to do. It's a lot more work, but if you understand and you can apply this, if the decimal piece gets smaller, the exponent piece gets bigger, it's now quite easy. And it's just going to be the same sort of problem over and over and over again. It doesn't matter what the problem looks like, it's going to be very similar. Add my decimal where I know it needs to be. This piece got smaller by 1 decimal place. 1 decimal place. Exponent gets bigger by 1 decimal place. And what is 1 bigger than -5? Hopefully you said -4, not -6. -5, if it goes up by 1, you add 1, it gives you -4. That's it. All right, so I did 2, you do 2. Here's letters C and D. I'll show you get them all on the page at the same time. There you go. Let's go ahead and pause the video. Try those 2 on your own. When you're ready to continue, hit play, and we will do it together. All right, let's see. So 5.245, the decimal needs to be here. We would only move the decimal 1 place, and this number here got smaller. It was a 52, it's now a 5.2, so it got smaller by 1, so my exponent gets bigger by 1, 7. This needs to be a 9.32. He got smaller by 2 places. Exponent gets bigger by 2 places, giving me +1. My brain shut down for a second. So -1, if you get bigger by 2, you do get a +1. Okay. Couple more practice problems. Now these guys all start with a 0 point something. So for some people, this would be a very different problem, but not for us. For us, it's the exact same problem, just 3.72. Put the decimal where you know it needs to go. Times by 10. This piece is now getting bigger. It was 0.3, now it's 3.72. It's a bigger number. It got bigger by 1 decimal place, which means your exponent is going to get smaller by 1 decimal place. And we're done. Put the decimal where you know it needs to be. 4.6 times by 10 to what power? Well, let's see. This piece is getting bigger by 1, 2, 3 places. So my exponent gets smaller by 3 places. And if you're not sure what 3 smaller than negative 8 is, negative 8, and you go down, you subtract, you go down by 3, gives you negative 11. Two for me, 2 for you. Go ahead and pause the video, give them a shot. When you're ready to continue, hit play. All right, let's see. 3.9 times by 10. He got bigger by 1, 2 places. Exponent gets smaller by 2 places. Should give you 10 to the negative 4th. Letter H, put the decimal where you know it needs to be. He got bigger by 1 place. It was 0.7, now it's 7.6. It's a bigger number. Got bigger by 1 decimal place. Exponent gets smaller by 1, which gives us 10 to the positive 4th. Okay, so now we've been able to do a bunch of converting, and we're going to take a little break from converting. We'll be back to it in the next example. But in this skill, we want to be able to figure out if the number we're looking at is scientific notation. That's it. That we just want to know, is the thing I'm looking at scientific notation, yes or no? And if it's not, circle the part of the expression that's wrong. So, for example, in this first one, I'm going to use my highlighter, actually. So in this first expression, this would be scientific notation if this was a number between 1 and 10. If this was a 1-digit number, 0.34 is not allowed. Letter B, is this scientific notation? My decimal piece looks good. My exponent piece looks good. Yes, that is scientific notation. Okay, so I want you to try that on these next two. I want you to figure out if they are in scientific notation and just either put yes, they are scientific notation, if it is, or highlight or circle the part of the problem that's wrong. All right, letter C is not scientific notation because this is not a power of 10. If that was 10 to the 3rd power, it would be scientific notation. Letter D is also not scientific notation because that exponent piece is wrong. It should be 4.2, not 0.42. Okay, a couple more. 2 for me, 2 for you. Letter E. Well, actually, both of these pieces are wrong. This would need to be like a negative 9.3. This would need to be 10 to some power. So almost the whole thing was wrong. Definitely not scientific notation. And it's the same problem in letter F. This decimal is in the wrong place. And that's not even a 10. It's not even a power of 10. That's 200. That's definitely not allowed. So that's kind of a pain in the butt. Okay, go ahead and try letters G and H. All right, letter G. Let's see. The decimal piece looks good. The power of 10 looks good. That one is scientific notation. Letter H. Decimal piece is no good. Can't have that. My power of 10 is fine, though. Okay, so now we should hopefully be able to, if we see a number, recognize if it is or is not scientific notation. That was the goal of these problems here. Example 4. This skill is now being able to go from scientific notation back into standard form. So we want to have no power of 10 left. We want to have commas and lots of zeros if that's what the problem calls for. Okay, so the way we're going to do this is basically the reverse of what we were doing before. It's going to be very much the same method. The difference is, instead of having 10 to the second power, we would like to get to the point where we have, and I'm going to use my highlighter tool, my ghost tool, we would like this to become a 10 to the power of 0. Remember how 10 to the power of 0, we were able to add it in those first few problems? I'm going to scroll up here in a second. Higher. All right. Remember how we added a 10 to the power of 0? And then this was our number in standard form? Well, that's what I'm going to try to get to. I'm going to try to get from this. I'm going to get my power of 10 to be a 10 to the power of 0, because that's just equal to 1. That's going to go away. That's going to vanish, which is why I just wrote it in highlighter. And then this other number, the decimal piece, will be in standard form. So if I can make this a 10 to the power of 0, then this other number out front here will be my number in standard form. So let's get to it. Well, to do that, my exponent is going to do what? Well, he needs to get smaller by 2. To make my exponent go away, my exponent needs to get smaller by 2. 2 minus 2 is 0. So if my exponent gets smaller by 2, what's going to happen to my decimal piece? Well, it's going to get bigger by 2 decimal places. So what is this number bigger? Well, if I move the decimal this way, it's going to make the value smaller. It's going to be like 0.002. We don't want that. If I move the decimal this way 2 places, I get 256. That's bigger by 2 decimal places. This is my number in standard form. I got rid of my power of 10. He is all gone. When I move my decimal to make that all happen, I got the number 256, and I can prove this to you. 2.56. Our calculator actually has a little times by 10 to the power of 2. Oh, I typed in 265 instead of 256, but you get the idea. It is correct. Okay. I would encourage you not to use your calculator for too much of this, because we're going to see that this skill, this scientific notation, is almost guaranteed to be a no calculator skill on our standardized testing, the PSSAs, at the end of the school year. Okay, so this is something that, I mean, just even this problem right here, that could be a no calculator question. So it'd be good to know how to do this without a calculator. All right, letter B. So I want to make this become a 10 to the power of 0. For that to happen, my exponent is going to get smaller by 8. So that means this exponent needs to get bigger by 8. So now which way would I move my decimal? Because right now the decimal would be here. It's 3.0. If I move it to the left, that value would be getting smaller. That might be like 0.00. We don't want that. That would be smaller. So we're going to go to the right 8 places. So actually, as I do that, I need to move this 3 over. So I'll use my ghost tool. 1, 2, 3, 4, 5, 6, 7. I moved it over 8 places, and all of these spots get filled with zeros. I'm going to double check quick. I moved over 1, 2, 3, 4, 5, 6, 7, 8 places. Okay. And the last thing to do to make this look like good, proper standard form is add your commas. Starting from the end, 1, 2, 3, comma. 1, 2, 3, comma. So that is now the number 300 million in standard form. All right. So go ahead and pause the video. Try these next 2 letters, C and D, on your own. When you're ready to continue, hit play, and we'll do it together. Alrighty, so we want this to become a 10 to the power of 0, so our exponent is going to get smaller by 4, which means this piece needs to get bigger by 4, and that would be, well, I'm going to move my decimal 4 places, and if I move the decimal to the right, the value gets bigger. So if I go 4 places, 1, 2, 3, 4, 3, 7, 4, 6, 3.8 is my number in standard format. And the only thing I'm going to do is I'm going to add a comma right here, because here's my decimal, 1, 2, 3, comma. Helps us see that that's the number 37,000. And that's it. Letter D, last of this type, I believe. Let's see. Oh, I want him to be 10 to the 0, smaller by 3. This side's going to get bigger by 3. So I'm going to go 1, 2, 3 places, 8, 3, 7, 0, add a comma, and we're done. I thought those were done. Now I think this is the end, or very, very close to it at least. So the difference between, those problems and the problems we're doing now is the exponents are negative. So that just means we're going to end up moving the decimal a different direction. But the process is the same. I want this to be 10 to the power of 0 to make it standard form. This piece now needs to get bigger by 6, because if you have -6 and you get bigger, you add 6 to it, you get 0. So it's getting bigger by 6 to make this go to 0, which means this is going to get smaller by 6 places. And when you're making a number smaller, a decimal smaller, you remove the decimal to the left. Think about it. If I go this way, 63, 632, 6,300, that's getting bigger. But if I go this way, 0.6, 0.06, 0.006, it's getting smaller. So I'm moving my decimal 6 places. 1, 2, 3, 4, 5, 6. Fill in all my empty slots with zeros. And there's my decimal. And most people put the 0 out front here. So it's 0.000006323 in standard form. Letter F, I'm going to scoot over because I can see I'm going to have moved my decimal 9 places. So he becomes a 10 to the power of 0. It got bigger by 9. This piece gets smaller by 9. And let's see what we got. 832. I'm going to move my decimal 9 places. 1, 2, 3, 4, 5, 6, 7, 8, 9. So here's going to be my decimal. 0.00000000832. Now, I've avoided talking about a very common mistake people make here intentionally, but I think we're going to talk about it now before I send you off to the next 2 problems. One of the biggest mistakes that students make in this lesson, and even in some of the problems we've already done, you see how we've been counting decimal places and I've been drawing my loopies. Well, some students get it stuck in their head that instead of counting decimal places, they count the zeros. And I want you to see, even from up here, that doesn't always work. Well, those problems don't work out for us. Here, there was not 5 zeros before the 3, even though we had to the -5th power. Up here, this is probably one of the only problems where counting the zeros actually worked. Oh, there's 3 zeros, there's a 3. There was not 7 zeros here. We didn't just go, 1, 2, 3, 4, 5, and put a 5. That wouldn't have worked. There was not 2 zeros here. There was not 4 zeros here. Okay, I'm telling you that now because it is an issue I see every year, and I want you to be cognizant. Big fancy word means I want you to understand that it's a problem and think about it as you're going through the problems to make sure you're not making that simple mistake. Okay. So here are the next two. These are the last two of this type. Go ahead and pause the video. Try them on your own. When you're ready to continue, hit play, and we'll go through it together. Letter G. So we want 10 to the power of 0. It gets bigger by 4. This piece is going to get smaller by 4. So 9, smaller by 4. 1, 2, 3, 4. My decimal is going to be right there. Every other spot is filled with a 0. And we're done. Letter H. We want it to be a 10 to the power of 0. Make the power of 10 go away. So that's going to get bigger by 2. That's going to get smaller by 2. So 7, 3, 3. I'm going to move my decimal 2 places. 1, 2. Fill the empty spots with zeros. And we're done. Do you see how its value is smaller than what it started? 7.3, 0.073. That's a smaller value than that by 2 decimal places. All right, our next skill here is being able to compare. Now that we are able to convert from one type of number to another, the next skill usually is figuring out, well, how do we know which number is bigger or smaller? If they're written in different forms, what can we do? And as you can probably guess, the way we're going to do this is by making them the same form. Either both in standard form, like this is standard form, either both in standard form, both in scientific notation. It doesn't really matter. Now, I have faith that if we put all these things into standard form, you would be able to do them quite easily. So here's what I'm going to do. I'm going to put these two numbers both into scientific notation to show how that comparison would work. Okay, so I'm going to add a times by 10 to the power of 0. To make this in scientific notation, I start here. Remember, this was the very first thing we did in this lesson? I know, that was 35 minutes ago, but that's what we did. And then this piece, actually, its decimal's already in the right place. It's 3.45. So in scientific notation, it would just be 3.45 times by 10 to the power of 0. So that actually is scientific notation now. So now comparing these two numbers. The way you compare two numbers in scientific notation is you look at the exponent. Oopsie. You look at the exponent. It is guaranteed the number with the bigger exponent has the bigger value. 100% guaranteed. So if two numbers have the same exponent, if they have the same exponent, then you have to look at their decimal pieces, the part in front of the times by 10. And usually there's a difference there. But if they have different exponents, whichever exponent is bigger is the bigger number. So in this case, -9, 0. 0 is the bigger number, which means that this number here has the bigger value. This number, because it's a -9, would be a 0.00000000832. I was actually counting zeros on my fingers. Okay, so this would be very small, where this is at least 3.45. Letter B. Why don't you go ahead and actually try letters B and C. So either you can make them both into standard form. If you like that, do that. You can make them both into scientific notation. But I want you to compare both these numbers, B and C, figure out which one's bigger and smaller. Pause the video. When you're ready to continue, hit play. We will go through together. All right, so letter B. I'm going to continue converting the standard form number into scientific notation. Now my highlighter is way too big. Times by 10 to the power of 0. This piece I want to be a 3.2 times by 10. It needs to get smaller by 1, 2, 3, 4, 5, 6. Smaller by 7 places, so my exponent gets bigger by 7. So I've got 3.2 times 10 to the 7th versus 3 times 10 to the 8th. In scientific notation, you look at the exponent. Boom, boom. 8 is bigger than 7, which guarantees that this number is the bigger number. Letter C. This, let's see, times by 10 to the power of 0. This is going to become a 4.5 times by 10. My decimal piece gets bigger by 1, 2, 3, 4 places. So my exponent is going to get smaller by 4. So I have this versus that. Ooh, those two are the same. It's 4.5 times 10 to the negative 4th, 4.5 times 10 to the negative 4th. They are the same, and hopefully you found that. Okay, so when comparing numbers in scientific notation, you look at the exponent first. If the exponents are the same, then you look at your decimal piece to compare. All right, we got a couple little quick problem solving, and then we are done. Letter A. How can you tell by looking at a number in scientific notation if it represents a very big or a very small number? And the answer is, you look at the exponent. If the exponent is, let me make my marker bigger. Everything's wrong. All right. So if it's like 3 times 10 to the 8th, positive exponent means this is a big number. The decimal, when I move it, is going to move to the right. It's going to become a bigger number. Where if I had 9.3 times by 10 to the negative 4th, if I have a negative exponent, that's going to be a very small number because the decimal would move this way, become 0.000 whatever. So big exponent, big number. Small exponent, by small I mean negative, exponent, it's a small number. Letter B. Mr. Einstein's class is studying how light moves. The speed of light moves approximately 671 million miles per hour. Express this number in scientific notation. All right. So 671 0 0 0 0 0 0 boom boom, and I'm going to add my times by 10 to the power of 0. I'm going to say, okay, I know this needs to become a 6.71 times by 10. My decimal piece here is getting smaller from 671 down to 6.71. Smaller by 1, 2, 3, 4, 5, 6, 7, 8 places, which means my exponent is going to get bigger by 8 places. Miles per hour. So that is the speed of light in miles per hour in scientific notation. Letter C. This one's for you. In the year 2000, Americans consumed an average of 47.2 pounds of potatoes and this many, 5.936 times 10 to the second, pounds of dairy products per person. Did Americans consume more potatoes or dairy products? Pause the video, try it. You're ready to continue, hit play. We'll go through it together. All right, so I mean, you got two ways. You can either have them both in standard form or both in scientific notation. I'm going to do standard form here because I think it makes a little bit more sense for us. So they ate that many pounds of potatoes. We know that from the beginning of the problem. The problem is that this dairy products is scientific notation. 5.936 times by 10 to the second power. So I'm going to rewrite that into standard form. So I'm going to make this a times by 10 to the power of 0. I'm going to make my power of 10 go away. To do that, my exponent needs to get smaller by 2, so my decimal piece gets bigger by 2. 593.6 is my standard form. So what was bigger, the pounds of potatoes at 47 or the pounds of dairy at almost 600? Yeah, it's definitely dairy. By a lot. Last question. Multiple choice. Which set of numbers below is written from smallest to largest? Now, before I send you off to do this problem, I want you to think strategically. I will help you eliminate one choice and show you why, and then maybe you can use that to fix or cross off some other choices. So letter D, I'm going to tell you right now, is very wrong. I know that because remember how we said in scientific notation, the size of the exponent lets you know the size of the number. The bigger the exponent, the bigger the value. The smaller the exponent, the smaller the value. Well, those exponents are all wrong. I mean, I'm going from smallest to largest. That is not the smallest exponent, followed by that, followed by that. That one's not the largest. So I know that letter D is wrong. Okay? So maybe you'll use that strategy to help you eliminate some other choices. So go ahead and pause the video, do this problem on your own. When you're ready to continue, hit play, and we'll go through it together. All right. So for the same reason we crossed off letter D, we could also cross off letter C. My exponents are definitely wrong. That is not from smallest to largest. So then that leaves us A and B. -5, 2, 6, -5, 2, 6. So the only kind of wild card number is this one. We have to figure out where he would actually fit in to make this work out. So what I'm going to do, since all the other numbers are scientific notation, I'm going to change this 0.04 into scientific notation. I'm going to figure out what it would be. So 0.004 to scientific notation, I'm going to add my times by 10 to the power of 0. I'm going to move the decimal where we want it to go. 4. I'm just going to put 4. It'd be 4.0, but 4 times by 10 to some power. Let's see. This piece got bigger by 3. 1, 2, 3. My exponent gets smaller by 3. So he's 4 times by 10 to the -3rd power. So that's a 4 times by 10 to the -3rd, or 4 times by 10 to the -3rd. So out of A and B, which of those has the exponents in the proper order? It's letter B. -5, -3, smaller, bigger, bigger, biggest. That one's correct, and that one's wrong. All right. Summary. How do you know whether to move the decimal to the left or to right when changing number into scientific notation? Well, you don't really move it to the left or to the right, right? You move the decimal between the first two digits. So I guess that's how you tell. You move it the direction of the first number. Sometimes you move it to the left if that's where the first digit is. Sometimes you move it to the right if that's where the first digit is. But really, you just put the decimal between the first two non-zero digits, and then from there you calculate if it got bigger or smaller. Okay. Thank you for watching this lesson on understanding scientific notation. Hopefully you learned a lot here, and we're going to expand on this knowledge in the next 2 lessons. Thank you for watching. Until next time, toodles.